Hey everyone, welcome back. Today we're diving into a groundbreaking approach to data communication that's redefining how machines understand information. Imagine a future where wireless networks don't just transmit raw data, but interpret meaning, like teaching a machine to grasp the essence of a message instead of just sending it. This is the power of semantic communication, and we're unpacking a cutting-edge study that's pushing this field to new heights. Let's get technical. Traditional communication systems are like sending a full cookbook to someone who just needs a recipe. They transmit all the data, but what we really need is the meaning. That's where semantic communication comes in. Instead of raw bits, we send semantically rich representations. Think of it as transmitting the idea of a cake, instead of listing every ingredient. But here's the challenge. How do we reliably send this meaning over noisy, bandwidth-limited wireless networks? Enter CLIP, a neural network that bridges text and imagery, acting as a universal translator between modalities. Unlike traditional systems that require constant training, CLIP allows the transmitter to extract meaning without prior training. The receiver then uses that semantic representation to train its own model for tasks like image recognition or reconstruction. It's like giving someone a puzzle piece and letting them infer the full picture. But wireless networks aren't perfect. Noise, interference, and limited spectrum pose real hurdles. The researchers tackled this with a reinforcement learning framework using proximal policy optimization, PPO. Think of PPO as a self-driving car learning to navigate traffic. It adjusts CLIP's parameters and allocates network resources in real time to maximize performance. The result? A 40% faster convergence rate, and 4 times the reward compared to traditional methods. Let's break down the mechanics. The CLIP-based encoder transforms images into semantic vectors, digital fingerprints capturing meaning. These vectors are then decoded by the receiver using a stable diffusion model to reconstruct or classify the original data. It's like a digital artist using a sketch to paint a masterpiece. But how does this scale in real-world scenarios? The study tested 3 CLIP variants: CLIP-YTB/32, CLIP-YTB/16, and CLIP-YTL/14. The latter, with its larger parameter count, outperformed others in noisy environments. Why? Its deeper architecture captures finer details while filtering out interference, akin to a high-resolution camera cutting through fog. The key innovation: a resource allocation framework that decouples semantic encoding from network coordination. Devices can extract meaning locally, send compressed vectors, and let receivers handle downstream tasks without constant back-and-forth. This reduces bandwidth usage and energy consumption, making it ideal for IoT devices or real-time video streaming. The implications are massive. From edge computing to autonomous systems, this research rethinks communication as a semantic process rather than a bitrate competition. By optimizing both AI models and resource management, it addresses wireless noise, spectrum scarcity, and energy constraints, 3 critical bottlenecks in modern networks. So what's next? This isn't just about better algorithms, it's about reimagining network design. By focusing on meaning over bits, we're paving the way for smarter, more efficient systems that adapt to real-world challenges. Thanks for watching. If you want to dive deeper into how semantic communication could shape the future of AI, hit subscribe and let me know what you'd like to explore next. Stay curious, and we'll see you in the next video.